All right, this is going to be the last video that we are going to be dealing with, and it is 1.9. It is hardware abstractions has to deal specifically with gates and logic, more specifically logic gates. So we're going to get into further detail with that. We're going to look at, so again, actually kind of rolling back this example here to kind of understand how the abstraction works from the hardware level. We start in the bottom of the screen here, and we have our transistor. And if we were to actually crack open the transistor and kind of look at its most basic level, we'd have this diagram right over here. All right, and that diagram is the schematic of what a transistor looks like, and a simple gate structure, if you will. If I were to abstract that idea into a diagram, so again, kind of taking a few steps back and looking at the bigger picture, what I would see is the diagram over here, and that is the diagram that we would use to symbolize, in this case, an AND gate. All right, and then this would be another example of a type of gate. This is called a flip-flop or a latch circuit, all right, which consists of AND or gates, depending on the type of flip-flop that it is. If I were to take a step back further, all right, I'm looking at the integrated circuit as a whole, all right, and that is nothing more than one chip or one piece of a bigger puzzle, if you will, which this is your random access memory. This is your RAM, the computer's memory. And then that is a integrated part that kind of fits into the motherboard of a computer system, and obviously has its own functionality. So as you can see, from the smallest piece all the way up to the largest piece, all right, we're kind of taking a step back. We're getting less and less detailed as we go, but the level of abstraction is getting higher and higher the more generic that we get. All right, and so that's an important piece in programming. And as we discussed so far, when it comes to abstraction, it's all about simplifying our code, making it simpler. Well, the same thing holds true for hardware as well. Abstraction is all about making the process or understanding computers or seeing how they function more simplistic. All right, so, and actually, let me get this out of here because I'm going to re-explain all this. So to understand, how this all works, this again goes back to the last chapter, which we talked about binary code. All right, and again, the computer system only understands how to read binary code. And again, we understand and interpret binary code as ones and zeros. But again, remember that the computer doesn't see it as ones or zeros. The computer sees it as voltage or current electricity flowing out of the gate, which would make it a 1, or there is no voltage or no current electricity flowing out of the gate, therefore it would be a 0. All right, and so the computer system recognizes that 1 or 0, whether if there is voltage or there is not voltage. All right, and to kind of understand that, we have to understand transistors and what their function are. All right, so in general, you have probably about anywhere from 100 to 300 million transistors in your cell phone devices or even tablets that we use on a daily basis, which is a disgusting amount of transistors. If you were to look at it from a computer perspective, I mean, you're talking in the billions, maybe 1.5, 2 billion transistors in computers nowadays. All right, and those are the fundamental building blocks, if you will, that make the computer, go, that make it what it is. All right, it is the circuit, the gate, that allows this electricity to flow in and out. Now, for the sake of I'm not going to go too detailed into these gates, but to kind of give you a little bit of background information, just as far as so you understand how this process goes. That's kind of what I'll give you a little bit of that information now. And so, as I said, inside of a gate, information is stored and processed as zeros and ones, all right? And they're registered as little bits of electric current. So transistors don't have any moving parts within them, which is extremely important because it's all a fixed mechanical system, if you will. And I use the word mechanical loosely. And so this is where the concept or the substance of semiconductors come into play. So we know that most semiconductors are made of pure silicon, all right? And that means that it conducts electric current better than any insulator. And if you remember, an insulator is something like plastic or rubber that doesn't allow electric current to flow through it. All right, but being that it's a semiconductor, the word semi is important because it means that it only conducts electricity partially. All right, it's not like a metal that will allow electricity to flow through it easily. All right, and then the reason for this is because the atomic structure of silicon, it has 4 electrons in the outermost of its valence shell. And if you remember from your chemistry classes, and for those of you that are chem majors, you can geek out all over this all you want, which is a good thing. But the valence shells are the outermost electrons that you have on the orbitals around the atoms. So this allows silicon to form bonds with its 4 nearest neighbors, therefore filling up, if you will, those loose electrons. So in general, it forms a tetrahedral crystal. But since all these electrons are kind of stuck within the bonds that it forms with its neighbors, all right, few of these electrons ever get loose enough to basically escape their bonds and travel through the crystal lattice, which is basically traveling electrons means that you have electric current. So having a small number of mobile charges is what makes the silicon of a semiconductor useful for what it is. All right. And so, but aside from that, all right, silicon in its purest form isn't that useful because when those electrons bond with their neighbors, all right, they're sort of kind of fixed in position and they won't sort of get loose and move around. So this is where the terminology doping comes into play. And I'm sure you've all heard the word doping before, especially in athletics, when somebody injects a foreign substance into their body. All right, that means you're enhancing overall, improving or enhancing the overall performance. All right, so in crystals, it's basically almost similarly exact, just the exact same. But we're doing it now on the atomic level rather than, physically like we would in somebody's body. So there are 2 types of doping structures that are available. They're called N-type and P-type. All right, so in order to make an N-type semiconductor, what you'd have to do is you'd have to take pure silicon and you'd have to inject a small amount of an element with 5 valence electrons. All right, and a good example for this is phosphorus. All right, and it's useful because phosphorus is similar enough to silicon in its structure that it could fit into the lattice, snugly. All right, with not a lot of issues that might come up. All right, but because of that, being that it has that 5th extra electron, it brings that extra electron with it. So this means now that in the semiconductor, it has more mobile charges. All right, so in turn, it can conduct better electricity in the long run. So the P-type of doping, all right, is an element that only has 3 valence electrons or 3 outer electrons. All right, so a good example of this is boron. All right, so what happens now when you have this differential between the N-type and the P-type, or the 5 electrons and the 3 electrons, this creates a hole, so to say. All right, and that's a place where the electron should be located, but unfortunately there isn't. All right, but this still increases conductivity of silicon because electrons can still move into it. Now, although the electrons that are moving, we like to talk about the holes moving around because it's obviously easier to think of a hole as a positive structure that is willing to receive an electron versus just electrons traveling to electrons. All right. But the reality is that both of the sides, the N-type and the P-type, are neutral, all right, because they do have the same number of electrons and protons inside them. All right. So the N and the P usually just refer to the sign of the charge that can move within them. So in an N-type semiconductor, it's negative electrons which can move. And in a P-type, it's basically the positive holes that we refer to. All right. But in actuality, they're both neutral. All right. So a transistor is made with both of the N-type and the P-type, just like a switch is. All right. And has an electrical contact on each of these ends. And it's called the source, all right, and the drain. One side the source, the other side being the drain. All right, so but instead of having a mechanical switch where we have a latch and we're kind of constantly moving a switch back and forth or flicking it up and down, all right, there is a third electrical contact that we call a gate. All right, so to look at this specifically over here, the gate would be something, these 2 lines that we see over here. Oops, let me get a different color. on this side and this side, these would be like equivalent to like your N-type and your P-type sides on your transistor. And this solid black line over here, that would be your gate. All right, so that would be like a good example of looking at both of those. All right, so the gate is usually insulated by a semiconductor, all right, and it's usually they use like an oxide to separate. So so it's not as conductive of material. So when the transistor is made, the N and the P types, all right, they don't expose themselves. All right, and so electrons will naturally diffuse from the N type, all right, where there's more of them, and they will travel into the direction of the P type to fill those gaps or fill those holes. All right, and then this basically creates what's called a depletion layer. All right, so what is being depleted? Well, charges that can move. All right, so there are more free electrons on the N type. All right, and the reason being is because they fill the holes in the P type. Now, this makes the P-type negative thanks to the added electrons. And this is important because the P-type side will now repel any electrons that try to come across. All right, so from the N-type. So that means, with the depletion layer, it actually consists or acts like a barrier, preventing the flow of those electrons or the electric current through the transistor. So right now, the transistor is in its off state, okay, because it's not allowing those electrons to go from one side to the next anymore. All right, and so that is obviously a very important step because that's what allows the transistor to pass that zero through because no electricity is flowing through it. So to turn it on, all you have to do now is apply a small positive voltage to the gate. All right, so in other words, the blue line that I have on my screen here, all right, what I'm going to do is I'm going to send a electric current through, and all I want to do is have a positive charge established onto this plate, because what that will do now, that will act as a conduit, if you will, attracting the electrons. And the charge itself will be great enough that where normally the previous layer would be depleted, therefore not allowing any further charge to pass through. Well, this charge that is now added onto this plate here, all right, what will happen now, it would create a potential difference, allowing the electrons to sort of get pulled through it. All right, and so that's basically, and I don't want to get, I kind of probably went a little too much into it, but I don't want to get any, more into it because you really don't need to at this level. Excuse me, further classes, if you were to ever take more advanced computer science classes, you definitely would get into this aspect of transistors and understanding how they work from a physics level or an electrical engineering level, and then also how this would then apply to the logic piece of it, the gates, and so on and so forth. And we'll talk a little bit about that as well. But again, I'm going to kind of cap it at that for now. But that's, again, the transistor and why they're important because, again, depending on their state, whether if it's electricity flowing through or not, is going to determine if it's a 1 or a 0. All right, so gates and flip-flops. So this is basically the terminology that we use to represent a gate. And we're going to look at, and I'm not going to explain it now, but we're going to get into these concepts in more totality in just a little bit. But this is basically some symbols that we use to represent gates. All right, and so when we look at it from an integrated circuit standpoint, the integrated circuit is nothing more than a series of all these types of gates and structures. All right, so this up here, or more so this down here, these two things, even though they're picture representation of what these substances are, there's countless, millions, if not billions, of these structures found on every integrated circuit that is printed by circuit manufacturing companies. All right, and so ultimately that will then allow us to understand abstraction that much more, because if we can understand how it operates on a single gate level, we now could then kind of take a step back and apply it to a microchip, which we then can now apply it to a more functioning component like your random access memory that you see on the picture here. And therefore, taking a further step back and understand how this abstraction gets farther back because that random access memory plugs into the motherboard and therefore has its own specific function of being that buffer, like I explained from a previous lesson. All right, so gates. So as it says over here, gates are just nothing more than a tiny, really small, at the most fundamental level, the smallest of circuits that are created on microchips. All right, and their purpose is to perform, as it said there, the basic logical function. Is it on? Is it off? Is it a 1 or is it a 0? And so to look at the three main types of gates, and there's a lot more than this, but we're going to focus on the big three. And the first one is the AND gate, all right? And just as you could see and follow along with this diagram, all right, the AND gate means that in order for this light bulb here at Q to light up, okay, the switches that I see here at A and B have to be in the on position. Because right now, both of them are set to being open, all right? And when a circuit is open, that means no electric current flows through it. So in order for a circuit to pass electricity through, it has to be closed, meaning that this switch needs to be closed and this switch needs to be closed. So when you think of it, if a circuit is open, nothing passes through, we basically say that it's open or it's a 0. When the switch is thrown closed, all right, that means a circuit is closed, and in this case, both are closed, then that means the result will end up turning, electricity will pass through, meaning that we're going to end up having a result of a 1. So when it comes to the AND gate, because of the fact that we need both A and B to be closed in order for electric current to show up at the light bulb Q, we have to now create a logic table, or we have to create a logical scenario of when that will make sense. All right, and so on the next slide, what we'll see is just that. So this is a truth table or logic table, call it what you will. All right, but what we see is we have a column for A, a column for B, and a column for Z, and Z is the output, which in this case is our light bulb. All right, and so what we're saying here is that in order for Z to be on and true with an AND gate, okay, both A and B have to be closed, or those conditions need to be met in order for us to return a value or for electric current to be passed through. So it doesn't matter if both are closed, if one is closed, the other is open, or if the first one is open and the second one is closed. All right, that is going to return a 0 or no current in either case because of the fact that one of them at least, or if not both, are open. They both have to be closed. They both need to be true in order to meet that criteria and therefore return a value of a 1. Okay, so that's how the AND circuits work, or the AND gates. All right, and again, like I mentioned earlier, we use, again, this symbol to represent an AND gate. It looks like a capital D, letter D. And again, we have two inputs, one input here, one input here, and then obviously the capital Z is your output. All right, and again, don't worry about this. I'm going to kind of go through that. One thing you'll see when it comes to abstraction, we can abstract even further. And as you notice with this diagram here, we have even a further abstraction. So in other words, we have a complex logic circuit here where we have 3 AND gates connected together. So this would be your input 1 and 2. And this would, or I should probably say A and B. And this would be like, say, AND gate number 1. This would be AND gate number 2 with inputs A and B. And this would be your AND gate number 3. In order for 3 to throw a 1, meaning electricity to pass through it, that would mean that both A and B on gate 3 has to be true. Or in other words, a value of 1 needs to be passed through them. Well, in order for a value of 1 to be passed here, that would then mean I would have to exit or output a value of 1 here. And in order to do that, I would need a value of 1 on both inputs, because in AND gate, you have to have 1 for each. And that would hold true also for number 2 as well. I would have to have electricity flowing in both ends to return a positive or to return a 1 on this end. Therefore, 1s will then be entered into here, and then I will throw a final result as a 1. If if the ones on the left-hand side here, gates 1 and 2, don't have a number 1 on both A and B inputting, then you're going to get a 0 as an output in the end. And let's see. All right, so let me just delete that arrow out, and then we'll move on to the next slide. All right, I'm going to skip over that. We'll go to the next gate. So the physical OR gate. So the OR gate is the next one. And as you can see, and for those of you that took physics already, you probably saw the AND gate as being what's called a series circuit. This would be an example of a parallel circuit. And what you see here is that instead of having one pathway for the electricity to flow, like in the previous one, to get to the end result, the bulb, all right, what we have here is what's called a parallel connection, which means electricity can flow through in this direction, or it could flow through on this branch and go through this direction. So if I hypothetically closed the switch A, but I left B open, well, the electricity would no longer flow through into the channel where B is located. It would stop there. But with A being closed, electricity could continue to flow through my circuit and then reach the light bulb, and the light bulb would light up. All right? What I could say is if I left A open, but this time I closed B, well, electricity would get to this point and would stop there. All right? But because circuit B is closed, it could flow in this direction and flow across that because the switch is closed, and then get to the light bulb and light the light bulb up. All right, so what we find in this scenario here is that both A and B can be closed and electricity will pass through, or A can be open and B can be closed and electricity will pass through, or B can be open and A can be closed, electricity would still pass through. The only scenario where that wouldn't happen is if both A and B were open. All right, and that's what we see with this truth table over here. With A and B being open, we get a value returned as a 0, meaning no electricity passes through. But as long as one, doesn't matter which one, in B, or if it's in A, or even if it's in both, as long as one of those latches or one of those switches are closed, all right, you're going to get electric current passing through the entire circuit. All right, and so that is the main difference between the AND gate and the OR gate and how they work. Again, very similar to the AND gate. This is the symbol we use. It's kind of like the letter D for the AND gate, but this time it's maybe a little bit more curved, maybe kind of more parabola looking, but it has that curved inside as well. All right, so that's the distinguishing characteristic between the two. Again, has two inputs, A and B, and then one output, Z. And again, the inputs, only one needs to be a 1. All right. As long as one of these inputs, A or B, is set to being 1, meaning electric current going through, you will get a value of a 1 to return on your output over here. All right. So that is basically how the OR symbol works. The last one is called the NOT gate. All right. And it's a little triangle with, and importantly to remember, this symbol that's on the outside over here, the little circle. This NOT gate is basically what it means is that whatever the output should be, it's the exact opposite. So if we have a NOT gate at the end of an AND or an OR gate, all right, and let's just say, for example, the gate should throw out an electric current, should return a value of 1. If we put a NOT gate on the end, it reverses that and makes that 1 a 0. Or if there's no electric current scheduled to come out, we throw a NOT gate there, it's going to reverse that, and we'll get a 1 on the way out. All right, so it's basically the inverse of what to expect, so to say. And a lot of times what we see are these abstractions of these symbols, but when we add the NOT gate to this, so this top one here we see is your AND gate, and go back to it. There we go. And so I can actually combine the NOT gate and the AND gate together. And so rather than having to draw like the AND symbol and then having to draw the NOT symbol after it, what I'm going to do is just combine the two. And I have the AND symbol, and then I'm going to just draw that little circle on the end, which is this piece right here. All right, and what that's going to do, that's going to create basically an AND NOT gate, or they call a NAND gate, N-A-N-D. And then we can do the same thing for the OR gate. All right, so rather than having this connected to this, right, we're going to combine the two. and I'm going to draw the OR symbol, and then I'm going to put a little circle on the end, all right, and that is what we call the NOR gate, all right. So this would be the not AND gate or the not OR gate, and that is basically what it means is that when we think about the results that are supposed to return when we use the AND or the OR gate, if we attach a NOT gate along with it, it basically is going to return the opposite value. All right, so the last piece that we're going to cover is the flip-flop circuit. And I'm not going to get too much into this because, again, I don't want to get too technical. It's not, par for the course. But just so that you know that this is basically a flip-flop circuit, or they call a latch. And this is what all the memory that when we store information for our video and our MP3s and photos and everything, papers and you name it, on computers or within our phones or whatever. This is basically what it is. There are billions and billions of these within our memory that we have in our devices, and it all boils down to these little latch circuits. And there's a lot more complicated latch circuits than this. This is just a basic one. But not having to go through and explain everything and have to, have you remember it because you don't have to. But basically, there's these are called set reset switches. And you saw that earlier in the diagram when you saw the little box. And you had an R and an S here. Right, and there was like little holes here, and you can go back to toward the beginning of the video, and you'll see that. But basically, that is the outside casing of what a latch circuit looks like, which is basically what we're looking at right now. And this latch circuit, all it consists of is 2 NOR gates, and the whole point is that when I apply voltage onto the set side here, what it's going to do, this latch system is going to set the value as a 1. All right, and when I do not apply voltage on the set, but this time apply voltage on the reset, what it's going to do, it's going to reset the latch, and it's going to make the circuit, instead of a 1, it's going to assign a value of a 0. Because the output that we have on this gate here is connecting, and it's becoming an input on this NOR gate here. And the output we have on this NOR gate down here on the set side is going to come around and be an input on the reset side up here. All right, and so whether or not a bit of a 0 or 1 is stored, electric current or non-electric current, it all depends on where the electric current is entering into the latch. On the set side, it's stored as a 1. On the reset side, it is stored as a 0. All right, so that is pretty much it. We're going to recap it there. That is going to wrap up our Unit 1. So if you have any questions, please let me know. But I'm going to end the video here. Email me if you have questions. Otherwise, have a fantastic day, everybody.